I'm Chris Gladwin, CEO and co-founder at Ocient, and I wanted to talk a little bit about what's going on in the world of analyzing and storing data, particularly as it relates to NVMe solid-state drives and the new compute-adjacent architecture that we've developed at Ocient. So first of all, what's NVMe? And this is really a big deal. NVMe solid state is really the first new building block in hardware since the beginning of computing time. Up until now, we've had bigger, faster, cheaper things like DRAM and spinning disk and network and stuff like that, but we've never really had a new building block. And NVMe is a parallel interface that's an industry standard that really is an industry standard in that everyone uses it and it works great. You can take different products and plug them right in on one side of the interface or the other, and it just works. So it's a great standard. And that standard had been under development for some time, and it's really architected to bring solid-state drives to life. Traditionally, spinning disk had a serial interface, different flavors of serial interfaces, but NVMe really needs a parallel interface. So there's a new interface for it. And it's optimized for this new generation of solid-state, and it really is efficient and scalable. So it's a great standard. And what we've seen is drives were first available in some volume in 2020. And so that's kind of the first time that software designers, software architects like those at Ocient could really take advantage of it. Behind the scenes of this interface is the solid-state drive itself. And what you're seeing is this relentless improvement that's been going on in capacity and performance. And it's driven by the fact that solid-state drives are all electronic. There's no moving parts, and it therefore is following Moore's law. And solid-state is early technology, so it's really moving at the pace of Moore's law, where it's doubling in capacity, every 18 to 24 months, and we'll do that for decades to come. And a lot of it has to do, you can see here how they're just able to cram more and more bits essentially in the same amount of space as these new technology generations come to market. So it's an amazing new capability that's really transforming how data is analyzed and stored. In addition to solid state, there's the technology parts of it, but also the price part of it matters too. And what we've seen in the market from 2014 to 2022, which is where we are now, is the cost per gigabyte of NVMe solid state storage has literally gone from $2 a gigabyte down to 13 cents a gigabyte. That's a huge transformation. It's a 13x decrease in price. And that's the kind of thing you see when a technology is early in its Moore's law curve. In addition to the solid state drive itself, you have to, hook it to a pipe that can handle this ever increasing capacity, and what the industry is using is PCI. So there's been progressive generation of PCI lanes that are the thing that connects solid-state drives to a server. And those have needed to keep up and have kept up, and that PCI just keeps getting faster and faster. So that's been instrumental in really taking advantage of what solid-state drives can do. And there's more of this in the future. So we've gone from PCI 4 to 3 to 4 to 5 and headed to 6, and there's no end in sight in terms of the size of the pipe that you can connect to a solid-state drive. In addition, the processor has to be able to handle this ever-increasing flow of data, and you can see the same thing's been going on there. Ultimately, what matters in these kind of massive data analysis systems is the flow, how much flow of data can get moved around, not just off the drive, not just through the PCI lanes, but in and out of the CPU. And essentially what you're seeing, CPUs are keeping up by having more and more cores in the CPU, and putting more and more PCI lanes on the CPU itself. So we've gone from 739 gigabits per second of data that you could push in and out of that CPU to over 10 times that amount is coming up. So we're just, we're going to 5,000 gigabits per second of data you can push or pull out of a CPU, which is 5 terabits per second, and that's going to increase again. So all these things are lining up to just deliver amazing kinds of performance. So if you then chart what's happening and compare that to alternatives in terms of how much data analysis per dollar you get out of different media, and that's what's on this vertical axis here, versus how much data storage you get per dollar on the horizontal axis, you can see that DRAM, NVMe solid state, and spinning disk have all been kind of moving along. These are Moore's law kind of a chart because it's like a log. And you can see that DRAM from 2011 to 2016 was moving ahead, as was spinning disk. And I put the NVMe solid state as a dash line because even though it was moving ahead, you really couldn't get your hands on it in volume. You could get a couple of lab samples from Intel or Samsung, but you couldn't really use it because you couldn't get hundreds or thousands of these. They just weren't available. The fabs, the high volume fabs, weren't up yet. So that's kind of where we were. And you had really three architectures that were designed around what was available in that 2011 to 2016 period and before, and really the 50 years before. One of those architectures to analyze data was in-memory databases. They've been around forever. They're fantastic if you can afford the DRAM. DRAM is still about $5 a gigabyte. That's pretty expensive, but if your data set can fit, really if you can afford to fit it in DRAM, loading it all on DRAM and analyzing it there is fantastic. There's also been over the past 20 or so years, spinning disk-based storage systems used as the back end for data analysis or databases really were dominated by the Hadoop ecosystem and all the different flavors of Hadoop. Those are, as you can see, relatively inexpensive on a storage capacity basis, but they don't really deliver much performance. So you could have a large amount of data and do a small amount of analysis. And then there was a third architecture, really two flavors, originally the massively parallel processing databases, and then now the newer generation of cloud databases, data warehouses. But they're fundamentally similar in that they use spinning disk for the storage tier, and then they separate compute from storage, and they load data into a compute tier, which is really DRAM based to do analysis. Those architectures are fantastic if you have a really elastic workload. You aren't always analyzing data. You're analyzing it sometimes, or if the amount of data that you're analyzing is small relative to what you're storing. They're really fantastic. But that's not what we're focused on at Ocient. What we're focused on is a different set of use cases. Use cases where you have really a hyperscale amount of data that you not only want to store, but you want to analyze. And you can't really afford the DRAM. DRAM's $5 a gigabyte versus 13 cents a gigabyte for solid state. And then you can't really use spinning disk because it's just too slow. An NVMe solid state drive is about 5,000 times faster on a number of IOPS per drive basis. So it's just not even close to fast enough. And you can't really use a data warehouse because it's the use cases we focus on are ones where you're just consistently hammering at the data, storing at hyperscale, but analyzing at hyperscale with consistent complex queries. And that's just not going to perform well and not going to be cost efficient or even close to cost efficient on a traditional data warehouse architecture that separates compute from storage. So we've designed an architecture that places the storage and the compute adjacent to each other, actually PCI lanes, parallel PCI lanes away from each other. And at the same time, what we've seen is as we've developed and brought this architecture to market is some really fundamental changes in the performance of data analysis and data storage for this different media. What you can see here is DRAM has really been stalled. It's a very mature technology. From 2016 to 2021, it actually went backwards in terms of the amount of capacity you could get, or amount of analysis capability you get per dollar. And it's projected to slowly move. Spinning disk has been increasing slightly in its capacity, but it really never again can get faster because it's really limited by how fast the platter spins, how fast the rewrite head physically move. These are not mechanical, these are not electrical, but they're mechanical phenomenon, and they just can't keep following Moore's law. So meanwhile, NVMe as an early technology has been surging ahead. This is log, and you can see it's been getting from 2011 to 2031 where it's headed, orders and orders of magnitude more price performant, both from a analysis point of view and a storage point of view. And that's the curve we're riding at Ocient. We've also brought some innovation to that, which when we introduced in 2021, that moved the curve. So instead of making multiple copies as a way of making reliability, we use encoding and decoding of data to make reliability. So that was able to essentially move our curve in terms of the data storage per dollar in a system like this. So we're super excited about the position of really following this NVMe track. There are other vendors, other architectures where you can replace the spinning disk with NVMe. But if it's a separate compute and storage tier, you don't really get to take advantage of it because you're going to load stuff in DRAM anyway to do your compute, and it ends up not really saving you money. compared to storing on spinning disk for those architectures. So we're really excited about where this architecture and where this technology is headed. To give you a specific of how that really rolls out, this is a comparison of our compute adjacent architecture on the right with other architectures where they're separating compute from storage. Even though we're a software company, if we do our job perfectly, we can only go as fast as the hardware. So we spend a lot of time understanding how fast hardware can go, not just from a latency point of view, but a throughput point of view and other things, because that's ultimately, like I said, if we do our job perfectly, that's how fast we go. So this just shows how fast hardware can go for these two architectures. So you can see in a elastic compute or separating compute from storage, so you deal with an elastic workload, those architectures have a network that sits between the storage tier and the compute tier. And in a system like this where you're analyzing data at hyperscale, you'd be surprised by how much of the CPU, both in the storage tier and the compute tier, is spent unwrapping and wrapping stuff in network packets. It's actually a huge part of what takes CPU cycles, which means cost, and it also slows things down. There's a lot of other things you might have to serialize and deserialize the data, on its trip. You have to basically take it out of the S3 format and wrap it into, relational, schema to put it in your compute tier. It just takes a while. And at best, if you are perfect at it, it's going to be 1,500 or so microseconds. You just can't move the bits faster. And you're shoving that through a 100 gigabit per second network connection. Even if it's 2 of those or 3 of those, it's still hundreds of gigabits per second. Whereas in our compute adjacent tier, we have 4 parallel PCI lanes between NVMe solid state drive and each compute core in that node that combines compute and storage into one. They're just simply a whole lot faster. From a latency point of view, instead of 1,500 microseconds, you're 100 microseconds away. And the throughput is also an order of magnitude greater, where you're getting, instead of 100, maybe a couple hundred, 300 gigabits per second, you're getting 1,500 or 1,300 gigabits per second out of the PCI lanes and the solid state drive. So it's just fundamentally an order of magnitude or more faster. And as a result, you're just going to see significantly better price performance for the workloads that we focus on, which are analysis at hyperscale with continuous analysis, continuous complex analysis. So then, just to give you a little peek into a little more detail of some of the other things you have to do to realize this performance and how different it is from traditional database architectures. A modern NVMe solid-state drive to go this fast requires a queue depth of at least 256 for full performance. And that number actually keeps doubling as the performance of those drives keeps doubling as well. So in the coming years, you're going to see queue depths of 1,000 or more, just crazy numbers. Imagine a system now where you've got 1,000 of these drives with a queue depth of 1,000 in the future. That's 1,000,000. That's a lot. The other things that you see other database architectures doing is when they move the data off the drive, they're really using the file system, and they move it through the kernel, they move it through the file system into user space and serialize and deserialize the data before they can even begin computing. That's just way too slow. Back in the days when you were pulling data out of hard drives, it didn't matter that it took so slow because you were waiting on the hard drive anyways, the spinning disk. But with solid state, you can't do that anymore, and we definitely don't do that at Ocient. You also really have to understand, to get these levels of performance, what's going on inside the CPU itself with regard to the L1, L2, L3 cache that's inside of the CPU. For the pace at which we're moving data around and analyzing data, you really have to be sensitive to what's going on there. Because and we do a lot of things to manipulate and optimize for the maximum efficiency, how things are moving through the cache layers. We also have to eliminate network throughput by placing the operations as close as possible. We think of the query plan, all the things that are going to need to happen to analyze a query, like a tree. And what really matters is what happens on all the leaves of the tree. And those operations are the ones you're going to do the most of. There might be 1 or 2 trunk operations at the end. That's not really your bottleneck. It's getting all the leaves done. And so we basically put all the leaves operations right next to all these leaf operations right next to the compute tier itself. And so if you've got some giant query that's some kind of ad hoc query that literally has to hit 1 trillion things to deliver that answer, we can do that in seconds. And the way we do that in seconds is all those leaf operations are as close as possible to the storage tier, because you are going to be pulling that much data out of the storage tier. A cache is not going to help you for a query like that. Finally, and it's definitely a lot of extra work. It's not easy, but these kind of databases at this kind of speed absolutely have to be written in a language like C++. That's what we use. I mean, if you did something like this in Java and you had just a second of garbage collection, it would be the amount of data that pushes through a system in a second like this would be a huge problem. That's just not a possible way to get to high performance. And then you also have to manage the load requirements. In systems where you've got trillion scale data sets that you're analyzing, you always have a continuous giant load of data coming at the system. It's never a static data set. There's always some massive flow, 100,000 JSON documents a second or something like that, or coming in the front door. All that's got to get loaded into the database in real time while hundreds or thousands of other queries are going on. That has to all be integrated so that you don't have some kind of giant performance hit during the never-ending continuous update of the data set. So just to give you an example of the kind of scale at which we're talking, typical Ocient 10-node system is 240 solid-state drives. Each of those drives does 1 million random 4K reads a second. So that's 240 million random 4K reads per second, which is pretty amazing given the cost of a system like that. That's like a supercomputer level capability in a server level price, at a server level price. Those drives will provide 13 terabits per second of throughput, which is just an amazing number. And what's physically happening if you're fully loading those, if your architecture is right, you'll do about 61,000 new parallel read tasks 4,000 times a second, just to give you a sense of like how physically fast this stuff is flowing. So where are we headed in the future? Just to wrap up, what we're seeing is, as we showed in those charts that we got from the hardware manufacturers that make these components like Intel and Samsung and others, is that solid state drives will continue to lower in cost. And right now, the cost of, and basically what that means right now is the cost of adding solid state storage to a system like this is the same cost as a traditional spinning disk, like a low cost tier like Amazon S3. So what that means is data storage costs on a high performance database will be lower than traditional low cost spinning disk storage systems. And that starts now. Right now that those curves are crossing over and they're going to be separating over time. And like I said, we can add storage to an Ocient system at a cost lower than S3, Amazon S3 object storage, which is considered a low cost storage tier. And you get 5,000 times the performance out of it. The other thing we're starting to see is the cost of solid state analysis will go down to where data analysis costs with solid state will be lower than DRAM, which is pretty amazing. And that's going to start around 2030, and 2030 is really only 8 years away. And DRAM then becomes just a caching layer to move data in and out of the CPU. You can think of it like an L4 cache. It won't make sense for large data sets to load them up into DRAM and to analyze because your performance improvement for doing it, you'll just load your data into solid state drive, access it to the NVMe interface, and then DRAM really just becomes like an L4 cache. It's just a part of the pipeline of data in and out of the CPU. So these are some fundamental and exciting changes we're seeing at Ocient, and it's really very, very, very fun to kind of bring that to the world, because this is probably the biggest change in hardware in the history of computing.